This podcast is proudly sponsored by Cronbach's Alpha, the grand alchemist of consistency. This isn't just a statistical coefficient, it's the mystical thread that weaves through your survey questions, daring to reveal if they are truly singing in unison or if some are merely humming off-key. Watch in a trance as this magical number emerges from the data, attempting to confirm whether your collection of items is a harmonious choir measuring a single, ethereal concept, or just a chaotic cacophony of loosely related inquiries. It's a true test of internal melodic alignment.
Welcome back to the deep dive as we continue our discussion on survey research.
So far, we've covered a lot of ground. We've laid the foundations, gotten into the nitty-gritty of designing the survey instrument itself, discussed the critical steps of sampling, data collection, and managing data with an eye toward quality and ethics.
Exactly. So we've designed our perfect survey on, let's say, MLS burnout. We've sent it out to a representative sample of lab professionals. The responses have poured in, and we've meticulously cleaned the data, checked for errors, and got it all organized. We're now sitting on this pristine but massive spreadsheet. It's a grid of numbers, codes, and text. And if you just stare at it, it tells you absolutely nothing.
That's the perfect way to frame it. That raw data set is pure potential, but it's not yet information. The topic for today's deep dive is the bridge that takes us from that raw potential to actual, meaningful information. We are talking about the first, most fundamental steps of data analysis.
This is where the magic starts to happen. Today, we're going to walk through 3 crucial stages. First, we'll talk about descriptive statistics, the basic tools we use to summarize and get a feel for our data. Then we'll discuss a vital checkpoint that's often overlooked, assessing the reliability and validity of our survey instrument. In other words, did our survey actually work the way we intended?
And finally, we'll move into the art and science of interpretation. How do we look at the patterns, provide context, and begin to tell a coherent story with the numbers, all while avoiding some classic and dangerous pitfalls? It's the journey from a spreadsheet full of numbers to an actionable insight that could actually improve life in the lab.
I love that. So let's start at the very beginning. We have our clean data set. What is the absolute first thing we do to make sense of it?
The first step is to create a map of your data. You wouldn't start a cross-country road trip without looking at a map first, and you shouldn't start complex analysis without first getting the lay of the land. This mapping process is done with descriptive statistics. The goal here isn't to test a grand theory yet, it's simply to describe and summarize the basic features of the sample we've collected.
And how we describe the data depends entirely on what kind of data we're looking at, right? Just like in the lab where the test we run depends on the specimen type. In survey research, our data generally falls into 2 big buckets, categorical and continuous.
Precisely. Let's start with categorical data. This is data that sorts people into groups. Think of nominal data, where the categories have no intrinsic order, like which department do you work in, chemistry, heme, micro, blood bank. Or think of ordinal data, where the categories do have a logical order, like an agreement scale. Strongly disagree, disagree, neutral, agree, strongly agree.
You can't calculate an average department, so we need different tools. This is where we talk about frequencies and percentages. They sound simple, but they are the bedrock of analysis.
They are. A frequency is the most basic building block. It's a simple raw count. We surveyed 500 lab professionals. How many work night shift? The frequency is the answer, 125. How many are certified by ASCP? 450. It's the absolute number. It's essential for understanding the basic composition of our sample.
But frequencies alone can sometimes be hard to interpret. If I tell you 125 night shifters responded, is that a lot? It depends on the total. This is why percentages are so powerful. A percentage standardizes that frequency. Telling you that 125 people work the night shift is one thing. Telling you that 25% of our sample works the night shift immediately gives you context and proportion.
It makes the data instantly comparable. If you run the same survey next year and 150 night shifters respond out of a new sample of 750, the frequency is higher, but the percentage is now only 20%. The percentage tells the real story of the changing demographic in your sample. For any categorical question, yes, no, multiple choice, department, shift, Reporting the frequency, the N, and the percentage is the standard, and for good reason. It's clear, intuitive, and the foundation for everything else.
Okay, so that handles our categorical data. What about the other bucket, continuous data?
Continuous data, or quantitative data, is anything that can be measured numerically on a scale. Think of variables like age, years of experience, or a score on a satisfaction scale from 1 to 10. For this kind of data, we can go beyond just counting and start talking about the data's center and its spread.
And the most common measure of the center is, of course, the mean, or the good old-fashioned average. You add up everyone's age and divide by the number of people you surveyed. It gives you a single powerful number to summarize the typical value. We might find that the mean number of years of experience in our sample is 12.5 years.
It's an excellent starting point, but the mean has a famous weakness. It's extremely sensitive to outliers. Imagine we're surveying annual income in a lab of 20 people. Most are bench laboratory scientists making between $60,000 and $80,000. But the lab director, who is also in the survey, makes $250,000. That one single value will pull the mean income way up, making it look like the average salary is much higher than what the typical laboratory scientist actually earns.
That's a critical point. The mean can sometimes be misleading. It tells you the center of gravity, but it doesn't tell you anything about how the data points are clustered. This is why the mean should almost never be reported alone. It needs a partner. And that partner is the standard deviation.
The perfect partnership. If the mean tells you the center, the standard deviation tells you about the spread or the dispersion of the data around that mean. It answers the question, how consistent are the responses?
Let's use a lab example. Say we have two different hospitals and we survey them on turnaround time satisfaction, rated on a 1 to 10 scale. Both hospitals report a mean satisfaction score of 7.0. If you just look at the mean, you'd think they are performing identically.
But now let's look at the standard deviation. Hospital A has a very small standard deviation, let's say 0.5. This tells you that almost everyone's responses were clustered tightly around 7. It's a very consistent experience. Most people rated it a 6.5, a 7, or a 7.5.
Now, Hospital B also has a mean of 7.0, but it has a huge standard deviation of 3.0. This tells you the responses are all over the place. You have a very polarized group. You have a bunch of people who are thrilled, giving it 9s and 10s, and an almost equal number of people who are furious, giving it 3s and 4s. The average works out to 7, but the story is completely different. The mean of 7 is not representative of anyone's actual experience.
That is such a crucial illustration. The standard deviation tells you how meaningful that mean really is. A low standard deviation means the mean is a reliable summary. A high standard deviation is a big red flag that you need to dig deeper, because the mean is hiding a more complex story of variation. So for continuous data, the mean and the standard deviation are the dynamic duo. You always report them together.
Okay, so we've mapped our data. We have our frequencies, our percentages, our means, and our standard deviations. We have a basic picture of what people said. It seems like we're ready to start interpreting.
Almost. There's a critical quality control step we have to perform first. Before we trust the numbers, we have to trust the tool that generated them. We have to ask the fundamental question, does our survey instrument actually work? This brings us to the concepts of reliability and validity.
This is something every MLS can intuitively understand. It's the same logic we apply to our analyzers every single day. We need to know that our instrument is giving us results that are both consistent and accurate. A survey is no different.
I love that analogy. Let's expand on it with a more common example, a bathroom scale. Imagine you step on your scale and it reads 160 pounds. You step off and step back on and it reads 190. You do it a third time, it says 145. That scale is not reliable. It's not giving you a consistent, repeatable measurement. You can't trust it.
Now imagine a different scale. You step on it and it reads 250 pounds. You step off and on again. It reads 250 pounds. A third time, 250 pounds. That scale is highly reliable. It's incredibly consistent. But if you know your true weight is around 170 pounds, that scale is not valid. It's consistently giving you the wrong answer.
And that is the perfect distinction. A good survey, just like a good laboratory instrument or a good bathroom scale, must be both reliable, meaning it's consistent, and valid, meaning it's accurate and measures what we think it's measuring. Without these, our fancy statistical analysis is just garbage in, garbage out.
Let's break down reliability first. It's about consistency. If we gave the same survey to the same group of people a week apart, would we get roughly the same results? One of the most common ways we measure this in survey research, especially when we have a group of questions that are supposed to measure one single idea, is a measure of internal consistency.
You're talking about the famous Cronbach's alpha. You see this reported in research papers all the time. You don't need to be a statistician to understand the concept. Imagine we've created a 5-question scale to measure lab safety climate. The questions might be about management's commitment to safety, availability of PPE, comfort in reporting errors, etc.
If that scale is internally consistent, if it's reliable, then a person who feels the lab has a great safety climate should, on average, answer all 5 of those questions in a positive way. A person who feels the lab is unsafe should answer all 5 in a negative way. The questions should hang together.
Exactly. Cronbach's alpha is a statistic that essentially measures that hang-togetherness. It calculates the average correlation among all the items in the scale. A high alpha, typically above 0.7 or 0.8, suggests that all your questions are indeed tapping into that same underlying concept. It gives you confidence that your scale is reliable. A low alpha tells you your questions are all over the map and probably not measuring a single coherent idea. It's like a bad QC run for your survey.
So that's reliability, our consistency check. But that's only half the battle. Now we have to talk about validity. Is the scale accurate? Are we really measuring lab safety climate, or are we accidentally measuring something else, like general job satisfaction?
And establishing validity is often more of a detective story than a single statistical test. It's about accumulating different kinds of evidence. Let's start with the most basic form, face validity.
This is the does it look right test. It's a gut check. If you have a survey that claims to measure satisfaction with the lab's LIS, and the questions are about the speed of the system, ease of use, and uptime, then on the face of it, it looks like it's measuring what it says it's measuring. It has high face validity.
It's a good first step, but it's very informal and subjective. It's the weakest form of evidence. So we move to something more rigorous, content validity. This is about making sure you've covered all the important aspects of the concept. It's about being comprehensive.
This is where you bring in the experts. Let's say we're designing a survey to measure competency in molecular diagnostics. We, as the researchers, might draft 20 questions. To establish content validity, we would then send that draft to a panel of subject matter experts, senior molecular laboratory scientists, supervisors, pathologists, and ask them, did we cover everything? Is anything missing? Are any of these questions irrelevant?
Their feedback is what establishes content validity. If they say, you have nothing in here about contamination prevention, which is a core competency, then our survey initially lacked content validity, and we need to add questions to cover that dimension. It's a systematic check to ensure you haven't left a giant hole in your measurement.
Okay, so we have face validity and content validity. But the most important and most sophisticated form is construct validity. This sounds academic, but the idea is pretty straightforward.
It is. Construct validity is about checking if your survey behaves the way the theory says it should. You're looking for a pattern of expected relationships. Let's say we develop a brand new survey scale to measure teamwork in the lab.
To show it has construct validity, we would need to demonstrate a few things. First, we'd expect that scores on our new teamwork scale would be positively correlated with other scores on pre-existing validated measures of things like communication quality and job satisfaction. That's called convergent validity. It converges with related concepts.
At the same time, we would expect that scores on our teamwork scale would not be correlated with things it shouldn't be related to, like, say, an individual score on a colorblindness test. That's called discriminant validity. It can discriminate between different unrelated concepts. By showing that our new scale relates to things it should and doesn't relate to things it shouldn't, we build a very strong case that we are in fact truly measuring the construct of teamwork.
It's a powerful process. So to recap this QC step, reliability, using tools like Cronbach's alpha,
tells us if our measurement is consistent. Validity, built through evidence from face, content, and construct assessments, tells us if our measurement is accurate and truthful. Only once we have confidence in both can we move on to the final step, interpretation.
Now we can finally tell the story. We've described the data, we've confirmed our tool was sound, and now we move from the what to the so what. Interpretation is where we transform the numbers into actionable insights.
The first layer of interpretation often comes from looking for patterns by slicing the data. A finding that 75% of employees are satisfied with the current scheduling system is a decent descriptive statistic. It's the what.
But it's not a deep insight. The real insight comes when we start segmenting the data. This is often done with something called crosstabs or crosstabulation. We compare the answers of one group against another. What if we break down that 75% satisfaction score by shift?
And we find that 95% of the day shift is satisfied, but only 40% of the night shift is satisfied. The overall average of 75% was hiding a massive disparity. That is an actionable insight. It doesn't tell you the solution, but it tells you exactly where the problem is. The interpretation is no longer, scheduling is okay, it's, our scheduling system is failing our night shift.
This is the core of so much good analysis. Don't just look at the overall numbers. Always look for those interesting differences between groups. How do new hires feel compared to veterans? How does the chemistry department's view on automation differ from hematology? How do ASCP certified laboratory scientists answer versus non-certified laboratory scientists? These comparisons are where the real stories are usually found.
But interpretation never happens in a vacuum. A number by itself is meaningless. To interpret it correctly, you need context.
A 70% satisfaction score is neither good nor bad until you compare it to something.
Absolutely. There are few key sources of context. The first is your original research objectives. Always go back to the question you were trying to answer. If your goal was to assess the impact of a new LIS, a finding about the quality of coffee in the break room is probably irrelevant no matter how interesting. Your interpretation should always be guided by your goals.
Another key context is benchmarking. How do our results stack up? Let's say we find our lab has an employee engagement score of 60%. Sounds a bit mediocre. But if we find out last year's survey had the score at 45%, that 60% is now a signal of fantastic progress.
Or if we compare it to external benchmarks like the average engagement score for hospital labs nationwide, and we find the national average is 55%, our 60% looks pretty good. But if the national benchmark is 75%, our 60% looks like a problem area. Context is everything. It turns a number into a judgment of performance.
So we look for patterns through segmentation, and we apply context through objectives and benchmarks. Finally, a responsible analyst must acknowledge the limitations and avoid some classic traps that can lead to completely wrong conclusions.
Let's talk about the number one all-time classic error, confusing correlation with causation. Just because two things move together does not mean one causes the other. This is a mantra every researcher needs to have tattooed on their brain.
Give us a lab example. Let's say we do a survey and find a strong positive correlation. Labs that have adopted a specific new automated chemistry analyzer also report higher levels of employee morale.
The tempting but incorrect conclusion is this new analyzer makes people happy. Buying it causes an increase in morale. The reality is probably more complex. It could be that well-managed, well-funded labs, which probably already have higher morale to begin with, are also the ones that have the capital to invest in the newest technology. The new analyzer isn't causing the morale. It's a symptom of the same underlying factor, a healthy, well-resourced organization.
That is such a critical distinction. Correlation points you where to look, but it doesn't give you the answer.
Another huge pitfall is confirmation bias. We are all human. We often go into a research project with a theory or a belief about what we'll find. Confirmation bias is the tendency to unconsciously look for and overemphasize the data that supports our belief, while downplaying or ignoring the data that contradicts it.
If you are convinced that the night shift is miserable
You might latch on to any small piece of data that suggests dissatisfaction and ignore other data that shows they are actually quite happy with our autonomy. A good analyst has to be disciplined and let the data speak for itself, even if it tells you something you didn't expect or don't want to hear. Be willing to be proven wrong by your own data.
And the last thing to always keep in mind during interpretation is your survey sample. Who did you survey? And just as importantly, who didn't you? If you were surveying lab staff about a new policy and your response rate was only 30%, can you confidently say your results represent the entire lab? Probably not.
You have to consider the possibility of non-response bias. It might be that the 70% of people who didn't respond are the ones that are most angry about the policy. Their silence doesn't mean they agree. When you're interpreting and presenting your findings, you have to be honest and transparent about the limitations of your sample. You report your response rate and acknowledge who is and isn't represented in your data.
So to pull it all together, we've taken this journey from a raw spreadsheet to a meaningful story. We started by mapping the terrain with descriptive statistics, frequencies, percentages, means, and standard deviations.
Then we ran our own quality control, checking the reliability and validity of our survey to ensure we could trust our data. We used concepts like Cronbach's alpha and assessed different forms of validity to build confidence in our tool.
And finally, we moved into interpretation. We looked for deeper patterns by segmenting our data, we provided crucial context with benchmarks and objectives, and we kept ourselves honest by vigilantly avoiding pitfalls like confusing correlation with causation and respecting the limitations of our sample.
It's a process that moves from simple to complex, from description to insight. It's how you take the jumbled voice of hundreds of respondents and distill it into a clear, credible, and often actionable narrative. And for us in the lab, this kind of research can be an incredibly powerful tool for driving real change, whether it's improving a process, advocating for better staffing, or making the lab a better place to work.
A perfect summary. We've really laid out the foundational steps of analysis. This gives everyone the tools to take a data set and begin to make sense of it responsibly.
It does. And that brings our journey full circle. Across a series, we've gone from the very foundations of survey research to designing the instrument, collecting the data ethically, and now analyzing and interpreting it. We've really covered the entire life cycle, from the initial research question to the final data-driven insight.
It's been a comprehensive journey and hopefully a useful one for any of our listeners looking to use this powerful tool in their own professional lives. We hope we've shown that survey research, when done thoughtfully, is a discipline that fits right into the quality-focused, analytical mindset of a medical laboratory scientist. And with that, this wraps up our series on survey research.
Thanks for joining us on The Deep Dive.
We'll see you next time.